In this lecture, we are going to look at network theorems as applied to AC networks. Network theorems are applied to AC networks using the same approaches as used for DC networks. The differences are that complex impedance is used in place of resistance, and voltages and currents are expressed in phasor form. In this lecture, we are going to discuss the superposition theorem, the Thevenin's theorem, the Norton's theorem, and the maximum power transfer theorem. When applying network theorems to the analysis of AC networks, the analysis methods can be divided into two: those for circuits with independent sources and those for circuits with dependent sources. In this lecture, we are going to cover only networks with independent sources. The steps followed when applying the superposition theorem to an AC network are: 1. Remove all other sources, leaving only one. 2. Calculate the voltage or current due to the remaining source and note its polarity. 3. Repeat calculations for voltage or currents due to each of the remaining sources. 4. Add the voltages or currents taking note of polarities to get the overall value for the element of interest. In this example, we want to use the superposition theorem to find the current that flows through the 6 ohm resistor. Let's begin with the current due to the voltage source E1. We open circuit the current source. Effectively, we remain with a series circuit. The current I prime that flows through the 6 ohm resistance is equal to the source current that flows from E1. We calculate it as 3.16 amps at 48.43 degrees. The current flows from the left to the right. Let's now proceed to calculate the current due to the current source I1. We short circuit the voltage source E1. Effectively, we remain with a parallel network. The source of current in the network is I1. The current through the 6 ohm resistance is calculated using the current divider rule. We obtain it as 1.9 amps at 108.43 degrees. The current flows from left to right. The two currents flow in the same direction. Therefore, the overall current that flows through the 6 ohm resistance is the sum of the two currents. We obtain it as 4.42 amps at 70.2 degrees. Let's look at a second example. We want to use the superposition theorem to determine the sinusoidal expression for the voltage V3. E1 is a DC source and E2 is an AC source. Let's begin with the voltage due to the DC source E1. We short circuit the AC source E2. We take note that under DC conditions, capacitances are open circuits and inductances are short circuits. Therefore, we open circuit XC and short circuit XL. This is the circuit that we remain with. The voltage V3 prime is effectively the voltage across the parallel combination of 3 kilo ohms and 0.5 kilo ohms. This parallel combination is in series with 1 kilo ohm and are supplied by the source E1. Therefore, we use the voltage divider rule to obtain V3 prime. We obtain it as 3.6 volts. To obtain the voltage due to the AC source E2, we short circuit the DC source E1. This is the effective circuit that we remain with. To obtain the voltage V3 double prime, we first determine the total impedance as seen by the source E1. It works out as 1.312 kilo ohms at 1.57 degrees. We then determine the source current IT that flows from E1. It works out as 3.05 milliamps at minus 1.57 degrees. The current IT divides into currents through R2, through XC, and through R3. Therefore, the current I3 is obtained using the current divider rule. It works out as 0.686 milliamps at minus 32.74 degrees. The voltage V3 double prime is obtained using the Ohm's law. It works out as 2.06 volts at minus 32.74 degrees. In time domain, the voltage V3 prime is equal to 2.91 sine omega t minus 32.74 degrees. The polarities for the two voltages are the same. Therefore, to obtain the overall voltage V3, we add them up. We obtain the sinusoidal expression for V3 as 3.6 plus 2.91 sine omega t minus 32.74 degrees. The steps that are followed when applying the Thevenin's theorem to an AC network are: 1. Remove the portion of the network across which the Thevenin's equivalent circuit is to be found and label the resulting terminals A and B. 2. Calculate the open circuit voltage across the terminals A and B. This is the Thevenin's equivalent voltage. 3. Set all sources to 0 and calculate the total impedance as seen from the terminals A and B. This is the Thevenin's equivalent impedance. 4. Replace the initially removed portion and use the resulting circuit to determine the quantities as per requirements. In this example, we want to find the Thevenin's equivalent circuit for the network external to the resistance R. The first step is to remove the resistance R and label the resulting terminals A and B. This is the circuit that we obtain. Effectively, it is a series circuit. The Thevenin's voltage is equivalent to the voltage across the 2 ohm capacitance. We obtain it using the voltage divider rule. It works out as 3.33 volts at minus 180 degrees. We go on to determine the Thevenin's impedance. We short circuit the voltage source. This is the circuit that we obtain. The Thevenin's impedance works out as minus J2.67 ohms. Therefore, the Thevenin's equivalent circuit is made up of a voltage source and a capacitance. The voltage source rating is 3.33 volts at minus 180 degrees, and the capacitive impedance is 2.67 ohms. This is the circuit after we have replaced back the resistance R. We can use this circuit to calculate voltage or current through the resistance R. Usually, we can do these calculations when R is varied. Let's look at a second example. We want to find the Thevenin's equivalent circuit for the network external to the branch A, B. The first step is to remove the branch and label the terminals A and B. This is the circuit that we obtain. Effectively, this is a series circuit made up of the impedances 6 ohm resistance, 8 ohm inductance, 3 ohm resistance, and 4 ohm capacitance. The Thevenin's voltage is equivalent to the voltage that appears across the branch that contains 3 ohm resistance and 4 ohm capacitance. We can use the voltage divider rule to calculate the voltage. It works out as 5.08 volts at minus 77.09 degrees. We go on to calculate the Thevenin's impedance. We short circuit the voltage source E1. This is the circuit that we obtain. It is effectively a series parallel network. The Thevenin's impedance is calculated and works out as 4.64 plus J 2.94. Therefore, the Thevenin's equivalent circuit is made up of a voltage source in series with a resistance and an inductance. The voltage source rating is 5.08 volts at minus 77.09 degrees. The resistance value is 4.64 ohms and the inductive reactance is 2.94 ohms. This is the circuit that we obtain after replacing back the branch that was initially removed. The steps that are followed when applying the Norton's theorem to an AC network are: 1. Remove the portion of the network across which the Norton's equivalent circuit is to be found and label the resulting terminals A and B. 2. Calculate the short circuit current that flows through the terminals A and B. This is the Norton's equivalent current. 3. Remove the short circuit, set all sources to 0, and calculate the total impedance as seen from the terminals A and B. This is the Norton's equivalent impedance. 4. Replace the portion of the network that was removed and use the resulting circuit to determine required quantities as per the situation. In this example, we want to find the Norton's equivalent circuit for the network external to the 7 ohm capacitance. The first step is to remove the capacitance and label the resulting terminals A and B. This is the resulting circuit. To get the Norton's current, we short circuit the terminals A and B. The short circuit also short circuits the 5 ohm inductance. Therefore, the circuit is effectively made up of a branch containing the 1 ohm resistance in parallel with the branch containing 2 ohm resistance and 4 ohm capacitance. The Norton's current is calculated using the current divider rule. It works out as 2.68 amps at minus 10.3 degrees. We go on to determine the Norton's impedance. We open circuit the current source and remove the short circuit across the terminals A and B. This is the resulting circuit. The circuit is effectively 5 ohm inductance parallel the branch containing 1 ohm resistance, 2 ohm resistance, and 4 ohm capacitance. The Norton's impedance is worked out as 7.5 plus J 2.5. Therefore, the Norton's equivalent circuit is made up of a current source in parallel with the Norton's impedance. The rating of the current source is 2.68 amps at minus 10.3 degrees. The resistive part of the Norton's impedance is 7.5 ohms, and the reactive part of the impedance is an inductive reactance of 2.5 ohms. This is the circuit after the 7 ohm capacitance has been replaced. Let's look at a second example. We want to find the Norton's equivalent circuit for the network external to the resistance RL. The first step is to determine the Norton's equivalent current. We remove the resistance RL and replace it with a short circuit. This is the circuit that we obtain. We notice that the short circuit also short circuits the 5 ohm capacitance. Therefore, the circuit is effectively a series circuit made up of the 3 ohm resistance and the 4 ohm inductance. The Norton's current is equivalent to the source current that flows from the source E. It works out as 4 amps at minus 53.13 degrees. We proceed to determine the Norton's impedance. We short circuit the voltage source and remove the short circuit. This is the circuit that we obtain. We work out the Norton's impedance as 7.5 minus J2.5. Therefore, the Norton's equivalent circuit is made up of a current source of rating 4 amps at minus 53.13 degrees in parallel with a branch containing a 7.5 ohm resistance and a 2.5 ohm capacitance. This is the circuit after we have put back the resistance RL. A Norton's equivalent circuit can be converted into a Thevenin's equivalent circuit. Likewise, a Thevenin's equivalent circuit can be converted into a Norton's equivalent circuit. The Norton's impedance is equal to the Thevenin's impedance. As an exercise and on your own, do these questions. 1. Convert the Thevenin's equivalent circuits of previous examples into Norton's equivalent circuits. 2. Convert the Norton's equivalent circuits of previous examples into Thevenin's equivalent circuits. For AC networks, the maximum power is delivered to a load when the load impedance is equal to the complex conjugate of the Thevenin's impedance as seen by the load. Alternatively, it is delivered when the load impedance is equal to the complex conjugate of the Norton's impedance as seen by the load. If the Thevenin's impedance or the Norton's impedance is expressed as RTH plus JXTH, then the load impedance at maximum power conditions is given by RTH minus JXTH. The value of the power at maximum power conditions is equal to ETH squared over 4RTH, which is equivalent to IN squared RN over 4. The power factor at maximum power condition is unity and the efficiency is 50%. In this example, we want to find the load impedance ZL for maximum power transfer to the load as well as the value of the maximum power. Basically, to get these values, we use the Thevenin's theorem or the Norton's theorem. In this case, let's use the Thevenin's theorem. We remove the impedance ZL so that we remain with this circuit. The Thevenin's voltage is effectively the voltage across the 8 ohm inductance. It is worked out as 12 volts at 90 degrees. We proceed to determine the Thevenin's impedance. We short circuit the voltage source so that we get this circuit. The Thevenin's impedance is worked out as 10.66 minus J8. Therefore, the load impedance for maximum power transfer will be equal to 10.66 plus J8. The power that is delivered to the load at maximum power conditions is equal to ETH squared over 4RTH, which is equal to 3.38 watts. Let's look at a second example. We want to find the value of maximum power that can be dissipated in the impedance ZL. We notice that the delta connection made up of the impedances XL may give us challenges when calculating total impedances using the series parallel reduction approaches. Therefore, we convert it into an equivalent star connection. This is the circuit that we obtain after the conversion. We can reconfigure it into the form shown so that it is easier to read and understand. We are going to use the Thevenin's theorem to calculate the value of maximum power at maximum power conditions. We remove the impedance ZL so that we remain with this circuit. The Thevenin's voltage is equivalent to the voltage that appears across the branch containing the 8 ohm resistance and the 3 ohm inductance. It is worked out as 8.54 volts at minus 16.31 degrees. We proceed to calculate the Thevenin's impedance. We short circuit the voltage source E so that we get the circuit shown. The Thevenin's impedance is calculated and is found as being equal to 0.72 ohms plus J 5.46 ohms. Therefore, the load impedance that will be required for maximum power transfer is equal to 0.72 ohms minus J 5.46 ohms. The power at maximum power conditions is equal to ETH squared over 4RL, which is equal to 25.32 watts. I recommend that you do these questions from chapter 11 tutorial questions before proceeding to the next lecture.